gravity, so the more matter is sucked in. This clump ultimately gave rise to our solar system. The chemical composition of the solar system suggests that the process got its initial nudge from the explosion of one or more nearby supernovae, which were themselves the product of massive, short-lived stars that formed in the same giant molecular cloud as the Sun. In fact, hundreds to thousands of other stars, ranging from a few percent of the Sun's mass to upwards of 10 times the Sun's mass, formed in the same cloud. From that point on, things happened very quickly, at least in the way astronomers reckoned time. After just 10,000 years, a luminous concentration of matter formed at the centre of the collapsing cloud. At this stage, the heat of the embryonic Sun was generated by gravitational collapse. Such objects are called protostars. As the gas collapsed, it swirled into a vortex, for reasons similar to the formation of a swirling vortex when water goes down a bathtub drain. The swirl flattened the collapsing cloud of gas into a spinning disk. In the outer regions of such a disk, the centrifugal force of the spinning gas mostly balances the tug of gravity, and gas orbits in a ring without much falling inwards. Closer to the proto-sun, though, friction slowed the spin and allowed gas, mostly hydrogen, to accrete onto the proto-sun. The proto-sun grew, and its increasing gravity pulled in yet more mass. This process happened so fast that half of the ultimate mass of the proto-sun accreted in only 35,000 years. At first, the proto-sun was shrouded in dust. The dust in question was composed of grains of various minerals, a variety of ices, and even some organic haze particles that can be synthesized abiotically from the gases surrounding the protostar. Sometime between 500,000 and 1,000,000 years later, the proto-sun became hot enough that its radiation blasted away the surrounding gas and dust of the giant molecular cloud, and as the dust cleared, the proto-sun would have become visible as a point of light to any astronomers observing the solar system from afar at the time. The flattened disk, however, had not yet dissipated. Today, astronomers can see numerous objects of this type in our galaxy. They're called T Tauri stars and are known by their wild variability and high output of X-rays. T Tauri stars are often accompanied by pulsating jets of material ejected from the disk. The disks that surround protostars and persist into the earlier parts of their T Tauri stages are called protoplanetary disks, because that's where planets are born. Formation of gas and ice giant planets. All this time, something interesting was going on in the outer reaches of the disk. The material of the disk was mostly hydrogen, with almost all of the rest, about a quarter of the total mass, made up by helium. But the key action was taking place in the remaining 1% or so, which is composed of heavier elements, mainly carbon, nitrogen, oxygen, magnesium, silicon, sulfur and iron. We'll learn how this stardust is made in Chapter 4. Some of the iron vapor condensed out into grains of metallic iron. Carbon condensed into tiny granules of graphite, the crystalline form of carbon used to make pencils. Other atoms joined hands to form molecules. Here, a lot of silicon got together with oxygen to make silicate, SiO3, which combined with other atoms to make a palette of minerals. There, the silicate got together with a magnesium atom to make a mineral called enstatite, which too condenses into a dust grain. Oxygen got together with the abundant hydrogen to make water, H2O. Out in this part of the disk, it was cold enough for water to form ice. The ice helped the small dust grains stick together to form dust bunny-like clumps, which aggregated to form pebbles. There are many ices, including methane, natural gas, CH4, carbon dioxide, CO2, ammonia, NH3, and the nitrogen molecule N2, which makes up most of the Earth's atmosphere. Many of these could only condense out in the further flung, colder parts of the disk. In a process akin to droplets of cloud water aggregating through collisions until the droplets are massive enough to form rain, the dust grains kept aggregating through pebble size and continued onwards to the point where the clumps had enough gravity to compress the fluff into a hard kernel which could resist the tendency to shatter upon collisions. Such objects are a kilometre or more in size and are called planetesimals. The process is like the formation of a cosmic deluge, except that instead of raindrops we have ice, rock, iron assembled.